Thank you for joining the Energy Storage at PNNL webinar series, where we bring in expert panelists to discuss various topics. Today, we're going to be discussing code-compliant energy or fire and explosion protection for energy storage systems. We would like to engage you in the discussions, so feel free in the chat window to go ahead and type in any questions. At the time that we have Q&A after each panelist does a short presentation, if you would like to make some comments, feel free to turn your camera on and introduce yourself as you're called upon. And so really, there are many experts that are participating in this call as well as the presenters, and feel free to share your experiences in this discussion. So without further ado, I would like to go ahead and introduce our esteemed panelists today. We have Paul Hayes, who is a fire protection engineer and general manager at the Hiller Companies, formerly American Fire Technologies. Lauren Kyer, who's the director of business transformation at the National Rural Electric Cooperative Association, and Andy Labe, senior engineer at Fluence. And without further ado, let me go ahead and pass off to Paul. Thank you.
Good afternoon, good morning, everybody. Depending upon where you may be at the moment, I'd like to thank Matt and PNNL for giving me 4 hours to talk about batteries today. Okay, well, maybe not 4 hours, but I've got 10 minutes, and I'm going to talk to you a little bit more about the explosion hazard. And this is one of my favorite pictures in the world, and I always show this out because of unintended consequences. But this was a power site that needed power, so they brought it out there, and apparently it caught fire, so somebody added a suppression system. Now, the unusual thing that we run into with batteries is that by suppressing the fire, we can make the explosion hazard worse. By addressing the explosion, we can make the fire hazard worse. So it's not always an easy solution of what is the higher risk. And a lot of the original codes were written around the fire hazard because that was the assumed failure mode. But then we started seeing some events in the world where the off-gassing produced explosion and people were hurt. So we decided, okay, let's look at it. How do we address an explosion? So the current code is giving you a couple of different options right now between what we need to do for an explosion scenario. But as we mentioned, well, what if we do a suppression? So if we're putting in a clean agent or a aerosol type product to suppress the fire, what we found is by increasing that suppression system that the gas so being produced and the batteries still propagate. So we're effectively moving it from a fire condition to an explosion condition. And guess what happens if we decide to vent or address the explosion? Well, we start moving air through the container, fire picks back up. So I've got some thoughts on that I'll express in a few minutes, but ideally the code is written right now to give us a better handle on the mitigation measures for explosion. We have 3 options. We can do a 69 approach, which says, let's get rid of the gas at the beginning on the onset, open it up, run air through there and move that gas out so that we do not get an ignition. The second option is an FPA 68 application. What that means is, okay, the gas is going to build up and we're going to allow it to explode or potentially explode, and we're going to try to mitigate the pressure wave, letting it out through openings in the container or cabinet through deflagration panels. Of course, the third option is actually run a test, see whether it explodes or see whether it burns, and then use that data. And obviously the real world trumps theoretical every time. So we're starting to see a lot of people engage with these large scale fire tests. So I think that's where the industry is going. It doesn't necessarily fit within the 9540A framework, which is obviously the basis that we utilize in order to try to design these systems. We start with that fire test. We do tend to be a little conservative, look at gas levels on a cell level. Then we also look at a mitigation measures, or looking through mitigating the module level through propagation. So tie the cell level gas production to the propagation at a module level and or rack, and see what those gas productions or fire hazard may look like. And an odd thing about batteries is a cell level tends to produce more gas. The module produces a little less gas because of the thermal mass. They don't tend to propagate as much. They actually perform better. And then a rack performs better than a single module, again, because of that thermal mass. So those are the three main requirements that we're looking at for how do we manage that. And as I mentioned, we're seeing a lot of clients out there in the world. We get called in as the fire protection engineer to evaluate the data and make some assessments. What is our risk? What is our approach? And as such, this is a good example of a large scale fire test. What I consider very positive on this is they lit the whole unit up and the whole unit burned. But if you look, what's right next to the batteries, they're in good shape. So we got up to 2000 degrees C in this container. The batteries next to us didn't get above 50 degrees C. And so that means they may not be viable coming out, but they certainly didn't propagate and they certainly didn't catch fire. And if you look at the spacing that we've got on this thing, there's only about 6 inches between containers. So I think this is a good thing for the industry. There's a couple of others that have done that large scale test as well. And we're seeing some very positive results. Yes, we lose one container, and there's a little bit of a, the philosophy for large scale test right now, Matt, is that let it burn. Well, that works well on remote locations. It's not the best in the world for urban environments where that's hard to do. But after watching a couple of these large scale tests, my philosophy is changing a little bit. I'm almost of the thought and mindset of encourage it to burn, make it burn. Because what happens when these things truly catch on fire and allowed to burn and we actually get a chimney effect, we open up the top of the container automatically. What we end up with is a 3 or 4 hour event. There's no stranded energy. The whole thing burns up. And that's a pretty easy situation to put a first responder in. They don't need to engage. They do not need to go out and fight the fire. They just sit back and watch. And one of my other mantras that I use is an asset is not worth a life. That's something easy for the fire department to understand. It helps them get a perspective. Those guys want to fight fires. That's what they're designed to do. And we want to tell them not to fight the fire, not to go forward with it, to truly let it burn. It's a pretty intense fire, but at the end of the day, if it burns up that quickly, maybe that's our mitigation strategy. We actually get away from the explosion panels. Tesla uses a sparker. So immediately on a failure, they ignite the gas and started burning. That might be a better option in the future. Now, I'm just throwing that on the table now. It's not something I don't think we've discussed a lot in the industry yet, but it's an option to think about. So Matt, that's just kind of a 10-minute overview on batteries and how I deal with explosions. I'll open it up to you and or the group if they've got any questions that they want to chase any of those rabbits.
Yeah, thanks, Paul. I appreciate that. Obviously there is, quite a bit in this area. And one of the things that you addressed early on, I think, is what I see as a significant gap in the codes. You mentioned the 3 different options for meeting the explosion control requirement. One is NFPA 68, which is essentially a deflagration vent. It directs the pressure. It takes an explosion for that to actually occur. The other one is prevent the explosion, NFPA 69. And the third one is an engineered cabinet that during the large scale fire test shows that no explosions occur. What I'll say is, the presence of a fire suppression system, as you pointed out in your great picture there, could actually present a significant issue if you are essentially sealing up the enclosure to allow, for example, an aerosol agent to work. You're not removing those gases. And so I think there's some conflict in the codes by allowing a clean agent system and potentially requiring a deflagration prevention system as well. So I think that's something that we hope in A55 to address. Any comments about that?
Yeah, so when we are designing a cabinet, when somebody comes to us and says, what can we do? What are mitigation measures? If they want a suppression system, because that'll work on an electrical fire, but not really on an electrolyte fire. So if we had an inverter, a power supply wiring, and put it out, wouldn't damage the batteries. So it's a little bit of a risk tolerance there. But what we require is a gas detector. And if we put out a fire and we see rising hydrogen levels, then immediately we switch. Even if we dump that clean agent 2 seconds before, we automatically switch over to a exhausting priority. Explosion becomes a higher priority than fire. We don't care about the agents that's in there. What we want to do is make sure we don't create a bomb. And to that effect as well, Matt, I'm gonna add a little bit more on the 68. We've done a lot of modeling and we've looked at it, and 68 works fairly well for kind of a bubble. So we've got a small pocket of gas inside the container that's maybe around the battery, and then it ignites. It produces a small pressure wave. Those vents work pretty well. What we found though is if you put in a full stoichiometric, meaning a perfect mixture of gases, of hydrogen, oxygen, and other hydrocarbons, if we fill a container and ignite that stoichiometric, they come apart. I mean, typically a container can handle maybe 3 to 4 PSI. Some of the models we've generated show 200 PSI. And of course, we got to bound it. So it's assuming they're solid walls, but nothing's going to survive that type of pressure wave. So it gives you a false sense of security that I got pressure vents out there, the 68, and that's going to protect me if it goes off. And that's not really a true statement. And I think, Matt, I'll throw out to PNNL right now. One of the things, you and I are looking at is what happens if we open the doors? Do we allow to not build up any gases that they would escape? What I'd say is we're probably going to move it back to the fire condition again. All right, even if we open that doors, we've got oxygen going in there. We're probably going to catch fire. So maybe there's a combination of opening the front, opening the top that might provide us some benefit going down the road.
Great, thanks. There's a couple of questions here that I wanted to allow you to respond to. Brandon asks, with the let it burn logic, he didn't recall any code language about fire watch requirements, and how do we assess stranded energy and reignition hazard for days or hours, afterwards?
Well, that's exactly why I'm sitting here looking at it. The large scale tests that we've done that have let it burn where we do not put any water on it, we are not putting any water on the adjacent units. But it is a perfectly valid question, because the fire marshal is going to say, well, we're telling them to keep it cool. Do not let things go beyond, the individual containers. Well, how do we explain to them that you don't need to put water on the containers full time? What we need is maybe wash them down every 2 hours, 3 hours. But with these large scale tests, we are letting them go and they are over in 3 to 4 hours. If we slow it down by putting water on it, they can be 6, 8, 10, 12, 24 hours. We get these long duration events.
Yeah, water, I always say, is a double-edged sword.
Yeah.
It's very challenging in this environment. Okay, that might have answered Greg's question. He was curious if water was applied for that burn that you shared on your slide there, and how.
Did not. We did not. No water. In the last couple of ones, we just have not put any water on any of them. We want to see how long the events are going to run if they're left alone.
So as you've already introduced that there is some examples of letting it burn that we're seeing from both manufacturers as well as some responders, emergency response plans. Is there any guidance that you're coming across or you're providing for manufacturers with respect to either putting it out with water or not putting out any water?
There is. That's something we look both in the emergency response plan as well as the hazard mitigation analysis, where we do a heat flux. If I don't have real world data, we look at what would happen if it was a fully engaged container. So that's one of my other favorite terms is zombie apocalypse. We can't design to that. We've got to design to a known and anticipated event. Well, a fully engaged container is a reasonably anticipated event. It's a bad day, but it can possibly happen if none of the other mitigations work. So we can do a heat flux study and look at how long will it take before that container goes up. And one of the things I really like here recently on some of these large scale tests is we're actually hooking the BMS up to the adjacent containers. So we can see the health of the batteries during the test. That is not a requirement of 9540A, but isn't that some great data to tell us how hot the batteries in the next container, not just thermocouples, but how hot the actual batteries are.
All right, that's great. There's quite a bit of interaction going on here, and I'm trying to just kind of pull some comments from them. There's one comment in here about whether or not anyone has included both 68 and 69. And one of the things I'll share is that I think 68 is, I think there's some problems with allowing 68 only, because it really is only designed to perform when there is an explosion. You could theoretically have an enclosure filled, above the upper explosive limit with hydrogen. And who's going to go open that door if there is no explosion? So while it is a passive system and there's some benefit to passive, I think that what we're seeing with some projects is people incorporating or looking to incorporate 69 and 68. And I think that's fine, but allowing only 68, not only is it challenging just because of the square footage of available roof space, it again, like I said, it's a after the fact protection.
It is, and even UL did some tests, even with clean agents and water, they all had deflagration events. It's just that pocket that builds up in corners and ultimately ignites. And I'm reading through some of the questions. Maybe I'll try to answer some, but I see some great questions and some great comments out there. So I like the way a lot of people are thinking here with this. So we appreciate that.
Yeah, thanks, Paul. And I think, I invite you to, engage these discussions as our next speaker comes up and keep the discussion going. So at this point, I'd like to go ahead and shift over to our next speaker. Paul, thank you so much for your comments. Lauren, I'm always messing up your last name, Kyer, correct?
Yep.
Thank you so much. So Lauren, please go ahead and take it away, introduce yourself and share your experience representing small utilities around the country with this topic.
Yeah, thanks, Matt. Thank you, the PNNL staff, for having me here. I'm Lauren Kyer, Director of Business Transformation here at NRECA. I am not a fire safety expert of any sort. What I am here to talk about is kind of my experiences trying to understand these codes. So I think some of the questions in there may help people at least hear from my experience. I have a few slides to share. So let me pull those up. So just to start with that, and I think, if I can see the slides. Oh no. Matt, can you see the slides?
It shows that you've started screen sharing, but I don't see any slides yet.
Okay.
Not a separate monitor?
No, 1 second.
I think we're having a little bit of an unstable connection with you, Lauren. I think what we'll do in the interest of moving forward is, Andy, if you don't mind, let's have you step in while Lauren can sort out her connection. And then we'll go ahead and just bring up your presentation. So Andy is a senior engineer with Fluence, has a lot of experience with burning batteries. And I think what you'll find is his experience and comments are quite interesting. So Andy, please go ahead and take it away. And Lauren will work with you in the background to get your presentation back up. Thank you.
Thank you, Matt. I'm Andy Leib. I'm with Fluence Energy. I'm a senior engineer over on the product development side of the house. And I've been in charge of the fire testing for about a year now. as we're going through this. So I'm going to talk a little bit today about UL 9548 testing and some of the additional testing that Fluence has conducted that goes above and beyond traditional industry standards. So this slide here's thank you to my lawyers. So just gotta have good disclaimers. So apologize about that. And then looking at the industry testing. So 9540A is a testing methodology that is utilized throughout the industry that really sets the standard so that every single player in the industry is testing the exact same way. That way, nobody's really engineering a test to have particular results one way or another. This testing is conducted at the cell level, module level, the unit level, and the installation level. So it's at every step along the way. Traditionally, you're heating a single cell and you're initiation methodology all the way through. So even at your largest levels, your unit levels, you're still only initiating a single cell and seeing the outcomes of what happens to that. So Fluence goes through our UL 9548 testing, just like everybody else, and been very successful with them thus far. On addition to that, we have taken it one step further, and we've gone to Fluence beyond industry standards burn testing. So what this is over here is a custom test that Fluence has done, where we've taken the heaters and we ramped them up by 10. So the power of our heaters was 10 times greater than what was utilized in the UL 9540A test, as well as instead of pushing a single cell into thermal runaway, we pushed 32 cells into thermal runaway. So I'm really excited to be able to show this. It's been a long time coming to be able to show a lot of this kind of information publicly. So it's really, really good. Additionally, we have the realistic field installation setup. So I'll talk a little bit about the testing setup down here in the bottom right. Our units, what we call them cubes, were installed with minimum field spacing. So that's 7 inches behind and adjacent and 7 feet across the aisle. So these are the tightest limits that are allowed in the field, as well as pushing our equipment above and beyond anything we would ever deem realistic in the field. So for our test that we conducted back in July, what we saw here was that it took us about an hour and a half for us to heat up and start to reach those first cell venting temperatures. Our fire alarm went off and reacted, and the notification system worked as designed and as planned. So that all happened well before any of this would have kicked off. That would have provided first responders with plenty of time to show up on site and react to the situation as necessary. The second kind of phase of the entire incident of the burn test was the off-gassing phase. So what we noticed is that our cells, as they were heating up, these were LFP, so lithium iron phosphate cells. As they're heating up, we're getting a significant amount of off-gassing. Now, this off-gassing continued on and off for about 5 or 6 hours until reaching about the 6.5 hour mark that it finally ignited, and we saw the flames grow. It started burning up away all of that, the toxic gases, as well as it spread through the entire cube. It burnt for about 6 or 7 hours, and then it put itself out. It's important to note that throughout this test, all the adjacent cubes that we had live modules in them. We were trying to figure out if this fire, if we push our equipment to extreme circumstances, if it would propagate to the next cube over. Additionally, there was 0 water put on any of this test. And then ultimately it just, the smoke at the end of the day just stopped. So it was really good. So here is some nice pictures for you to watch. On the left-hand side is the setup. We had our initiating cube, our adjacent cube, our behind, and then across the aisle. So we had 3 target cubes that surrounded it entirely. Again, smallest spacing possible. Throughout the test, we had the off-gassing. You see that white gas that's really indicative of a lot of battery fires. You can see that coming out of the cube down at the bottom and through the door. And then at the top right there, you can see that was the moment of ignition of the fire igniting. So most likely reaching auto ignition temperatures of some of the gases or some of the materials that are down and around that bottom left-hand corner. And then ultimately it burnt away for several hours. And then at the end of the day, there was no cube to cube propagation. It was very successful. a lot of damage around in the area, but everything was very safe, and it was a very controlled manner the entire time. So some of there was one comment in the chat that was about how do we make these tests kind of a little more cost effective as the batteries grow larger. My comment back to that was we collect as much data as we possibly can for these tests. This particular test, we had 95 thermocouples, 7 heat fluxes, about 7 video cameras, an infrared camera. We even had a drone flying around during the test collecting it. And then we were also pulling gas sampling data out inside the cube and above the cube during and throughout the test, and sent all that off so we can understand exactly what is going on and at what points in time it is going on throughout it. Fluence has taken significant steps in order to make our testing methodology even better. Again, following through with UL 9540A, but then just adding additional data acquisition systems on top of it so we can capture at every single thing that is going on. And we're able to best inform first responders and best inform our product design and best inform everybody in the industry about what is actually going on during these thermal runaway events. This is one of my favorite pictures on the right-hand side. I call it my Rubik's Cube. It's the nice thermal imaging of our cube after the fire. So it's one of my favorite parts. And then some of the key learning and significant takeaways for first responders. The biggest thing is don't approach, don't let it open. As Paul said, let it burn. My biggest thing that I like to tell everybody is just be patient. These thermal runaway events can be very unpredictable, and time is on our side. As long as we're able to sit there and watch it and monitor it, it's on our side. I'm a huge fan of thermal imaging cameras. They're great to help us to know what is going on. We don't always have cameras on the inside of every single enclosure. Therefore, we need to utilize tools on the exterior of our equipment in order to best understand what is going on inside. So with thermal imaging cameras, it's not necessarily those nice still shots that I had on the last slide, but it's more the trending of the data. And so we can understand, is it still heating up or is it cooling down? And if it's cooling down, then we know that the entire event is hopefully trending downwards into a more safe manner. And we can kind of wait until those temperatures reach a more closer towards ambient levels or as low as we can get them before we send somebody up to approach the container. And again, definitely keeping in mind the explosion hazards and how the gases could potentially build up, and taking lessons learned from in the real world and in the field of make sure we're keeping everybody as safe as possible throughout these very unpredictable events. And then really overall from a hardware perspective, just kind of limiting what is the impact to the equipment itself. So first responders are most important. Second, or really kind of last in our mind is protecting the rest of the equipment here and minimizing downtime overall for the customers. So in the case of one of these events, as you can see, you'd be 1 to 3 cubes that would ultimately need to be replaced. You'd have minimal downtime for the unit as a whole, and just really keeping the impact to the equipment side also as safe and as minimal as possible. And I believe, Matt, that's everything I have there. So if you'd like to jump in.
Yeah, Andy, first of all, thank you to you and Fluence for expending that expense to get this data. It's really critical. Not a lot of smaller manufacturers can bear this cost. And so I think some of the larger manufacturers have, a real advantage to the industry. This is validating a lot of, just personal thoughts that I've had over the years about where this industry might go. And so this is really good data. Key points: no explosion occurred. Fire was essentially contained to the unit of origin with some essentially cosmetic damage to the neighboring units.
Yep.
A couple of the real key questions that were raised by some of the folks that I know on here who I'm glad have asked really has to do with some of the toxic emissions. And I know that you really didn't measure that in this test. Is that correct? Or did you do any?
For this test, we were able to pull some very limited samples. So we had a very limited gas sampling setup. However, for our future testing and some of the stuff that we're working on, we have taken the gas testing up to another level. And I'm very, very excited to be able to present and talk on that. I'm not able to talk about everything about that just now. Just got a lot of the initial results and data, and we're combing through everything. But we have taken this up to real-time monitoring through FTIR, through GCTCD gas monitoring for all hydrocarbons, all toxic chemicals, and all carboalkaline metals. So we'll be able to monitor all of that real time. I'm very, very excited for some of the gas testing that we're putting forward.
That's an area that I think there's going to be a lot of work in the next 2 years on. NFPA Research Foundation is starting some work on some emissions measurement. And I think it's important to measure against baseline fires, what typically would be exposed. But there is definitely some concern on some of the heavy metals, in particular, whether or not specific cleaning requirements for PPE might be needed. And so in terms of stationary energy storage, the recommendations for responders to stay away is supported by how these incidents are evolving. I think that where they become less comfortable is when propagation continues to occur. So this is some good data. Andy, I'll ask you to go through the really active discussions going on in the chat, and I really applaud everybody for reaching out. I'm really hoping we can get to most of these questions in here. We've been successful in getting Lauren to join us again by phone. And so, Andy, thank you so much. Jump on your keyboard and see what education you can provide to those questions. But Lauren, please share your knowledge and experience with us. I think you're muted right now.
Can you hear me?
Yes, we can. Yeah.
Okay, great. Thank you. So sorry, everyone. My apologies. I apologize. The webinar recording will be a little bit choppy. I'm not going to share any slides. I think that was the culprit of technology's woes. So I'm not sure how much you heard, so I'm going to start from the beginning, and I apologize. Again, thank you, PNNL, for having me here. The reason I am here, I am not an expert on fire code safety, is I am with Matt's help and with Pacific Northwest National Lab and Sandia National Laboratories help, have been working through these standards. So in 2020, NRECA was able to be awarded some research money to look at deploying battery energy storage for critical infrastructure critical infrastructure for resiliency. And so we put there were 4 projects. There are 4 projects. 2 projects were at cooperative native service territory, and 2 projects are going to be on federal property military bases. And so with that in mind, we were able to, I guess, blessed actually to have Matt as our technical advisor on that. And the reason that I'm here is I work for small utilities that are a little bit newer to the battery energy storage space. Cooperatives across the country have deployed a little over, give or take, 70 different types of projects, mostly with a microgrid configuration. Normally, it's going to be a generator plus a battery to help sustain a critical load or work with a large commercial and industrial member of ours. And the reason that I'm here is that the 2 military-based projects needed another level of compliance. So if I'm talking to the utilities out there, one lesson learned, and that's kind of why I'm here, is put your codes and standards that you want the manufacturers to be to meet in your RFP. 2020, as Paul and Matt and Andy have stated, came out when we decided to deploy these projects. And so they were new compliance codes that they had to meet, that the manufacturers have to meet. And I think that there's a lot of confusion, and I know there was from my perspective. So I think lesson 2 is understand the difference between an installation code and a product code. You could any manufacturer could put a battery on said shelf, if you will, and that's because they meet some sort of product code. But once it gets installed, that's a different product, a different code, the installation code. That I think that there's a lot of questions around that. So I think lesson 2 is understanding the difference between the product code and the installation code, understanding that many states have not adopted these new standards. Cooperatives, like most utilities, have a culture of safety and believe in using the most recent and most up-to-date standards, and that's what we used here. lesson 3, be prepared that your projects may take longer. These standards, as Paul and Matt have noted, are new and are continuing to evolve. And that means that there's an education opportunity for the utilities involved, for the EPCs involved, for the manufacturers involved, for the integrators involved. And what Matt and I have learned through this process is that there's still a lot of questions and there's still a lot of education opportunity to be able to give to these folks. Because understanding that, you know, if you're putting a battery near an occupied building, that could mean something different. And that actually leads me to my next lesson learned. Understand where you're putting the battery, understanding where you put the compliance codes. So for example, like, as I mentioned, we're putting them on military bases. So besides just the NFPA 855, there are other codes that the military and the federal government require for battery storage. Those are new. They actually came out when we were working through the project. And so I think understanding the compliance requirements up front is really going to save you time and save you money. We, as I mentioned earlier, are deploying these projects. 2 of the 4 are done. The other 2, we are moving through that process, but it is taking a lot longer just because we need to make sure that they can meet those requirements. And what does that mean? You know, the utility, our co-ops wanted to see the cell data, the module data, the rack data. They needed to understand, you know, they needed to be able to see the fire code report. And so these are important things as a owner and operator of these battery energy storage systems. It's important that you understand what you are entitled to see, and to work with your AHJ or the authority having jurisdiction. One of the things that we plan on doing with these battery projects is, and we've been doing with them, is doing for, I think I saw on Andy's slides when I was able to join back, is that we are doing first responder training for our utilities and for the fire staff that's nearby, and for on the military basis for the military fire staff that is nearby, and ensuring that everybody understands that what Matt and Paul said, let it burn, and understanding what that means and what is there. So we are doing those trainings as part of the commissioning process of these batteries. And I think, you know, and I hate to say this, but when in doubt, talk to Matt and his staff. He is very knowledgeable and can fill in a lot of those areas of codes, and they are very complicated and very confusing. And as the co-ops are going to own and operate these, it's really important to think about how much you want to be involved from the beginning, or who are you going to rely on for that involvement. Again, there's a lot of confusion around these standards because they're so new, that it's important that you take the time to understand them. There's a really good graphic that Matt has put together for us that looks at the installation codes and the product codes. I unfortunately don't want to share my screen because I'm afraid that it will kick me off, but I think it's to spend some time on that. I know that I've been seeing a lot of discussion about NFPA 8, NFPA 68 versus 69 versus alternative method. Our method, I think, is going to be adjusting the cabinets. We are not going to be, and Matt can correct me if I'm wrong there, we will not be going down the 68 or 69 route. We will be going with the tweaking the cabinet design to be able to prevent some of this explosion control, to provide explosion control. And so, yeah, the reason, and I think it's really just important, you know, this is always changing. So come to the, and I'm going to be kind of a good spokesperson for the National Lab here. Come to the National Lab. You know, they have a great energy storage launch pad where they're keeping all this information and keeping people up to date. But as the owner and operator, you have rights to see these fire reports, to see these explosion reports, and you should ask for them. One of the questions we asked early on is, can we see your cell data? Can we see your module data? Can we see your rack data? And then, you know, be able to analyze what was that, you know, thermal runaway challenge or what could it be? I think that's really important to think about. As the battery storage industry continues to grow, I think it's just really important to just know that your safety fire codes at your state may not be up to date. And so I would always encourage, which is what our co-ops choose to do, is pick the most recent fire code, fire standard, to ensure that you're meeting the requirements, the best requirements that are out there. There's a question in here about how should AHJs in the code review alternate explosion protection systems. You know, there's going to be a lot of, and I'm sure Matt and Paul can talk about this, there's going to be a lot of fire departments that are not familiar with batteries and stuff. So they're going to really rely on the utility and their team to be able to tell them that. You know, I think the thing that we work on is we provide AHJ all of the codes and standards that we are familiar with and how we're going to meet or mitigate some of those challenges and have those conversations early. So we reached out to our AHJs really early into these battery projects just to ensure that they had skin in the game and understood, you know, what was going on and can provide input before we're too far down the path to roll it back. So I think getting your AHJ involved early, I think would be really important. Making sure that you understand the difference between an installation and product code, understand where you're putting this, you know, if it's near, you know, people, you know, if it's near a building that has people, that may mean more standards and more costs. And so I would, you know, as you're going down this battery energy storage road, just keep in mind that all of these things come with costs. And so that you should be aware and be prepared to adjust budgets, adjust timing, just to meet these codes and standards. Matt, did I get all that right? I think I did, but.
Yeah, that was great. That was great, Lauren. Let me just ask you a question. You know, you've definitely been, you know, between a rock and a hard place where you're really trying to get these projects built. You know, RFPs are being designed, citing all the right codes and standards. Manufacturers are getting selected. And then very late in the game, the manufacturers are recognizing that their understanding of the codes is challenging. And, you know, I've been there with you. And I guess I would ask, you know, do you see, what have you learned through your experiences in some of these projects that could potentially help the next project? What you know, what would you do different?
I think, yeah, because we did the RFP, we did the vendor interviews, we did the correct process. Now that I fully understand, well, I don't fully, but now that I have a better understanding of these fire explosion tests, those will be in the RFP. I'm going to need to see your cell module rack and explosion test data at the RFP level. I'm going to need you to explain to me that you understand what this means. I think that there is a lot of learning opportunity in this area, specifically for utilities, owners and operators, for manufacturers, for integrators. There's a lot of learning and education. So I think now that I understand that, I would become very smart on the codes and standards I want to put into the RFP, and I would make sure that I spend a substantial amount of time in the vendor interviews talking about this standard, understanding what they've done in this space, understanding that they understand what this is. It worked out for us because this is a research project, so we all get to learn together. But that is something that I think I would do differently, is now that I know more, is have those conversations really early into the conversation to understand where those pain points are going to be.
Great. Thank you very much. So, you know, at this point, as I try and get a feel for a lot of the questions, interactions, a lot of them really are technical focus around the explosions, the tests that Andy and Fluence performed. And, you know, one of the comments from, you know, someone I respect quite a bit, Kieran Claffey from Southern Company, you know, he's of a little different opinion, which I'm not saying he's wrong at all, which is this position of a defensive posture and the let it burn approach, no water. You know, it's their position is that they can't make that call yet because we don't understand the risks from the plume. So, you know, that's why I say water is a double-edged sword. You know, we could have a runoff contamination issue if we're using water. We could have a toxic emissions issue if we're allowing it to burn. So that's why I had mentioned earlier on that there's a lot of research Southwest SWRI is doing some research. NFPA's Research Foundation is doing some work on these emissions. We really need to better understand these to help make that call. So Kieran, thank you so much for commenting on that. And so I think what I'd like to do at this point, if all of the presenters just want to turn your cameras on, join back in the room here. And, Andy, thank you so much for jumping in and answering some of these questions here. I don't have a good grasp myself on what questions we've not answered that folks are really feeling. And of the participants, which there are a lot in the room, if you'd like to raise your hand, if you feel that we've not addressed your question, that's one way we can try and address it. But of the presenters there, is there anything that you're pulling out of this discussion that you want to touch back on or comment on?
No, it just all the amount of questions that we got. Matt here just says, the industry is still anxious to learn, and there's a lot of great questions in here. The one that stood out to me, Andy, and I'll punt it back to you, was the question about why didn't it explode with the gases? And I answered that very quickly, but I think maybe you can give a little bit more insight on that as well.
Yeah, no, I appreciate that, Paul. I think I dropped a quick note in there somewhere, but for this particular test, ultimately what we saw is that we blew right through the upper flammability limits and the upper explosion limits. We did have sparkers for this particular test. It's not a normal part of our design, but we were trying to ignite the gases in that test. Ultimately, as we were watching it, we saw we had real-time data for the oxygen, the O2 levels that were inside the container, and they went from 20% to 0, and it just went, and it was a nice cliff. And so that's kind of what we ended up with, and that's why ultimately the flame started on the outside of the cube and worked its way all the way towards the inside. So that was this test.
Sorry, Andy. Sorry.
Oh, I would say, somebody else brought up a really good point of repeatability of all these tests. And again, these are just very expensive tests. And every single opportunity we get to perform one of them, it's just an exercise in collecting as much data as we possibly can. So I think just more thermocouples, more heat flux sensors, more gas data. I always ask for as much as I possibly can.
Actually ask Andy a question. So you all chose to do this, right? As you just said, it's very costly. You chose to do this. I'm going to repeat that one more time. And why? Right? I hope I know the answer, but these are very expensive. What was you all's reasoning behind being proactive, which I think is great?
That's a really good question, Lauren. Really to drive the industry forward. These are really important topics, and these are really important things that we're doing. And ultimately, batteries are dangerous, and we need to make sure we fully understand the safety of them. And so we need to push them to their limits. And I think the industry as a whole right now, as we've all kind of acknowledged, is very young and immature. And every single chance that we get to drive the industry forward and kind of set that next level of standards is a great opportunity. So yeah, to push the industry forward and to do better.
I'll add that the lack of repeatability is one of the often cited concerns around 9548. You burn one, let's just say it's a residential product. You burn one, that's it, it's done. The results of that dictate whether or not it's safe to stack them together next to each other, use them indoors. And I think that test is really just a propagation resistance test. It really isn't a fire test. Although some have really been, ringing that bell for some time. And Paul, I'm going to acknowledge a comment that you've made, and I regularly, repeat this, that what we really want to know is, one, what is the propagation resistance of the module? Because that is important. We can't rule out a single cell failure, and we want to prevent it from propagating. But we've seen in real life that some of these thermal runaway events have been much larger than we thought. So there was propagation. So we want to understand then what is the risk of a larger fire. And the third is a deflagration test, and that requires igniting that gas plume. And so if you have a battery some of these cells are getting very large, approaching 300 amp hours, and the volume of gas from one cell easily puts you in an explosive range in many enclosure sizes. And so if we don't ignite that to test whether or not it will explode, then that's a big blind spot for this industry. So I hope to see a little bit more robust testing. You're doing it, unrequired, and that's where industry leads. And so again, kudos to Fluence for spending the money on this, but we do need to see the ignition of the gas plume. And so there was a comment in there earlier about there's a proposal for 9540 to require the ignition of the gas plume. Personally, I think that should be done. Obviously, it completely changes the test now. Now you have radiant energy from a flame, but we need to understand that. And some manufacturers are taking that approach to putting an igniter in an exhaust plenum as their deflagration control. And I think that it's worked fairly well for the couple of incidents that have occurred out there. So,
yeah, Matt, I think part of it is the code committee's driving the testing standards. We may not always be able to get it through UL or whoever the NERDLs are, but if we put in those requirements in the code for things like toxics, things like explosion and safety studies, I think it's going to be kind of a convergence that both of us have got to drive to that point, but that's still 3 years out. So the best we can do is to share that data, and I appreciate Andy sharing that today, because I think it is critical for all of our learning. There's too much stuff that is not presented because of the secret sauce. I can't share my data because somebody else might find out about it. But more and more people are starting to do bigger tests. And I think one of the most promising things we're seeing out is we're not seeing propagation to adjacent containers. And I think that is critical to the health of the industry, that we put it out there that if we do tell these guys to let it burn, they're not going to see a field of 100 containers go up.
Yeah, Matt, I wanted to add to that. I remember when we first started our journey, there was a TIA about container versus enclosure. And so we spent a lot of time, again, good education opportunity, to teach our manufacturers, right? And so I think to Paul's point and to your point, the codes have already changed since we implemented that in 2020. There was a TIA you had mentioned to me earlier today. It's now part of it. I don't know for the audience, you may want to describe the difference there. I think it may be helpful. It was helpful for me.
Yeah, good point. And for those, on the call, the TIA that basically included cabinets in the requirement for explosion control is now part of the 2023 NFPA 855. A TIA is a change that once the technical committee votes on it, it's approved, it's essentially enforceable when you've adopted that or referenced that 855. And so it was missed by many manufacturers, realizing that their cabinets now have to provide that. And some are still getting up to speed with that.
Yeah, Matt, I think the committee didn't necessarily see the change from the larger containers to the smaller one coming in 3 years prior. And it was never meant to be excluded. So when we looked at that and realized that some of the manufacturers were going, well, it doesn't explicitly say cabinets, so it must be purposely excluded, which was never the intent of the code. That was an easy one. We just went back in and stuck the word cabinet in there and said, okay, it's meant to be there.
Right.
So, Matt, I want to answer Keith's question. So when I receive these batteries, all of the fire safety systems will be built into the cabinet enclosure, whatever you would like to call it. I will receive it on site with everything already in there. And then when we do commissioning, we will run tests. But I think, Keith, to your point, from what I expect to receive it all already prepackaged in the system when I receive it.
One comment I have is, you can't protect everything all the time. I don't know if anyone's seen the picture of the energy storage system on the flatbed trailer. I think it was in Korea, caught fire on the highway. Right. So obviously there is no fire protection systems. It's not designed with passive fire protection. And so, we do the best that we can. And I think we have to maintain some perspective of where protections are required. Lauren, I read that question a little differently. I was looking more at storage, and there are some requirements for storage of batteries in 855 in chapter 14, I believe it is. So that does give some guidance for those facilities that are collecting batteries, both new and off spec. And that's a very important one. The industry that's really getting hit very, very hard is the recycling and the salvage industry. There's been a tremendous loss of property from materials recycling facilities due to batteries that shouldn't be in the waste stream ending up in there. Okay.
Matt,
Yeah.
Are we coming up on something, or?
No, we got about 5 minutes. I'm just trying to also
Okay.
peruse our comments and questions to make sure that we address
I
them.
was going to comment on some of the failures out there in the world, and some of them I defined as successful failures. We didn't see propagation, even
Yes.
things, a couple of the Tesla events here recently. I categorize those as successful failures. Nobody was hurt. We didn't have the whole thing go up. It mostly reacted the way it was designed due to 9540A. And so I would consider those a win, because we're going to have failures.
Paul, that's a really good point. And to Andy's kind of summary of what they found, I live 30 minutes from Moss Landing. The design of that first phase system, being an indoor system, resulted in a significant loss of power from the California grid. And that's one of the challenges with an indoor installation. And so I think to that point where you can segment the loss to the grid, that's a real key in these project designs. So yeah, thanks for triggering that. Maybe like another 2 or 3 comments or questions here before we start to wrap it up.
Matt, have you shared our information or contact? I didn't know if everybody wanted to share their contact, but there's just so many questions here that we can't answer. I don't know if it's worthwhile posting. I don't mind sharing.
Yeah, you know what, panelists, would you please just put your email in the chat? I don't think we have an individual slide with your contact information, but I think that the organizers of the web series can reach out to all the registrants with that as well. But just for right now, go ahead and do that. I think at this point, what I would like to do is to just thank each of you so much for not only the work that you're doing in this space, but for sharing your experiences today. We've had a really good attendance, and that's the goal, just to share the knowledge, help each other along, reach out to each other. There's a lot of experts in the room here in this chat, and everybody has taught me a lot as well along my path. So thank you to all 3 of you. I really appreciate that. I would like to just take a minute and let everyone on here know about the upcoming webinars that we have. The next one, which is on February 9th, is about power electronics and energy storage as an enabler. We've got some real industry powerhouses here. Our own Charlie Vartanian as a moderator. Leo Casey from Google X project has a real interesting perspective and background. Representatives from utilities as well on this one. And then on March 9th, we're going to bring up the topic about long duration storage policy and economics. Many have said that trying to put the value on a long duration storage product is really the challenge. And so I'm actually looking forward to this discussion. This will be moderated by Jeremy Twitchell from PNNL. So please, put these register for these. All of these webinars have been very successful with a lot of great content and presenters, and really appreciate all of you attending these and contributing to them as well. So any last comments here from our organizers? Did I miss anything in plugging our events? Silence is.
Thank you, Matt. Appreciate your
Thank you, Matt.
moderation.
Thank you, everyone. Have a great afternoon, evening, and we'll see you on the next one.